Now let's have a look at how to graph hyperbolas. They've got this basic form, y equals something over x, where the something, in this case a, is just a constant or a number. Now you can also rearrange them. You can see that here if I multiply both sides by x, then I'll end up with xy equals a. Now this form can be hard to recognise, and some students find it hard to recognise that this is the same thing. So be on the lookout for both. I actually like this method of looking at it because it reminds me that the x and the y value, when they're multiplied together, will always equal that one constant. So the one I've chosen to graph first, I've chosen to graph y equals 20 over x, purely because the factors of 20 should be really familiar to you. And we know that if we are going to multiply the x and the y together, and we're always going to get 20, you can see here why I've picked x values for my table of values of 1, 2, 4, 5, 10 and 20, because I know that they've got nice integer pairs that will give me nice easy places to plot. So when x is 1, y will be 20, whereas when x is 20, y will be 1. Similarly, if x is 2, y will be 10, whereas if x is 10, y will be only 2. And then when x is 4, y will be 5, but when x is 5, y will be 4. So you can see that when we join up the dots here with a smooth curve, because remember that these functions are made up of an infinite number of dots, and they're so close together that they just become a line, we get this basic curved shape. Now, what would happen if x gets bigger and bigger and bigger? Imagine a really big number like 1,000. We would have 20 divided by 1,000, wouldn't we? So we're going to get a smaller and a smaller fraction. It's never going to equal 0, even though it's going to get mighty close. So what we end up with is an asymptote again, which we draw as a dotted line along our x-axis. What's going to happen as x gets smaller and smaller? For example, what would happen if I said, let's let x equal 1/100th? Well, 20 divided by 1/100th is a really big number. It's going to get infinitely large, so it's going to keep on shooting up this way, and it's going to get closer and closer to the y-axis, but never actually meet it. So we also have an asymptote running along the y-axis, which you can show as a dotted line that way. Now let's consider what would happen if we had let all of these x values be negative. Well, if we've got 20 divided by a negative number, we're going to get the exact same numbers, but they're all going to be negative as well, aren't they? And that means that we're going to get the exact same shaped curve repeated down here, because when x is -1, y is -20, and so we've got the same thing happening but over this way. So that's the basic shape of our normal sort of hyperbola. Now, how can we vary it? Well, we can vary it by changing the value of a. So here I've used a nice big value of a like 20 just because the factors of 20 are so familiar to us. If I was to graph something like, say, y equals 1 over x, now if I make a table of values here to see what it would look like, let's just make the first few. If x is 1, y is 1 over 1, that's 1. If x is 2, I've got a half. If x is 3, I've got a third. If it's 4, I've got a quarter, etc., etc. And obviously if x was really small, like say a quarter, then y would be 4. So the points on this curve, if I was to draw it in red, are going to be very much closer in to the axes, aren't they? But they're going to give that same basic shape. So when x is 1, y is 1. This one is right in here. So it's going to be a graph that looks sort of like this. We'd have to really zoom in to see it in more detail. It's got the same basic shape, but it comes in much closer. So I think of it as having sort of a skinny waist, if you like. And if we let the number at the top be much bigger, let's go for something like bigger like 100, well then we're going to have it with a fatter waist. So if we were to graph that, then just thinking of some points, if we let x be, say, 10, then y would be 10. So it's going to come out to here somewhere as its midpoint. And it's going to have the same basic shape, but it's going to have a much sort of fatter waist, I guess you could say. So this one is y equals 100 over x. The black one was y equals 20 over x. And the red one was y equals 1 over x. So you might like to write a sentence that a larger value of a makes for a fatter waist on your graph, but they're all going to have that same basic shape. All right, let's consider what would happen now if we had a negative number for our a. So let's graph perhaps y equals, let's go -4 over x. Now, easy way to do this, just draw up a simple table of values for your first few things so you can see what's happening. If x is 1, y is -4 over 1, which is just -4. If x is 2, -4 over 2 is -2. If x is, well, let's not do 3 because it doesn't divide so nicely. Let's do when x is 4, y is -1. Now I can see a little bit of a pattern. If x is 1, y is -4, that's down here. If x is 2, we've got -2. We're going to have this sort of arrangement. Now 4 is not a very big number, so it's got a fairly skinny waist, this one, compared to some of the big fat ones that I drew. But you'll notice it's down here. And what happens if we let x be negative? Well, if x is negative, y won't be. And that means the other arm of this hyperbola will be up here. So I've labelled our blue one there as y equals -4 over x. Now, how are we going to remember this? Well, if you divide up your Cartesian plane into quadrants, we generally call this one the first quadrant, second quadrant, third quadrant, and fourth quadrant. That's just how we name them. We always start over here. Then we could say that if a is a positive number, in other words, if this number up here is positive, then the two branches of our curve, because it always has two branches, either here and here or here and here, they're going to sit in quadrants 1 and 3. So that's the normal type, the positive type. Whereas if a is negative or less than 0, then the two branches are going to sit in quadrant 2 and 4. Now, one other point, we don't label intercepts because in this case there aren't any, but we've got to make sure that we draw our asymptotes in. So put something on your drawing here to show that you are going to draw your asymptotes as dotted lines. Now, you don't have to label it on your picture as an asymptote, but maybe just make a note to yourself, always draw the asymptotes in. And then the other thing we need to do, similar to our exponential curve, to sort of lock in the scale here, because we can see that these things are actually all the same basic shape. And in fact, if I zoomed right in, and you can graph these on Desmos and then hit the zoom button, if I zoomed in to the red curve, we'd get to the point where it actually looks exactly like the green one that I've drawn. So they're all basically zooming ins of each other, if that sort of makes sense. So we want to kind of lock in the scale somehow, and the easiest way to do that is to always just label a point that's on each branch. So that locks it in. So if I was labeling a point on this one, y equals 100 over x, I could just pick a point, say 10, 10. When x equals 10, y equals 10. If I was labeling a point on this, y equals -4 over x, just pick a point, any point, doesn't matter which one. I might choose to label this point here, the point 2, -2. It's up to you which point you label, so just let x be something, sub it in, see what y is, write it as a coordinate pair. So it shouldn't be too much of a stretch then to be able to recognise one of these hyperbolas. You're going to really see that those asymptotes, which we draw as dotted lines, stand out, and they've got that really distinctive shape of having the two branches. So if you need to find the equation actually from the graph, working the other way around, you know if you see this basic shape that it's going to be in that form. So just sub in a known point, the x and y values, to find that missing number, that a. So here I can see that a known point is 1, 3. So if I let x equal 1 and y equal 3, now I just need to solve that little equation, multiplying both sides by 1. Clearly I can see that a equals 3. So this is obviously the curve y equals 3 over x. And double checking with the other known point, if I sub in -1 here, I get -3 there, which makes sense because 3 divided by -1 would be -3.